Hi everyone. In the last video, we talked about why do we even need classification of elements and also spoke about various attempts that were made to do so and why they were rejected. In the end, we spoke about the Mendeleev periodic table and also how it was very famous at its time because it was able to classify a large number of elements and also able to predict the existence and the properties of various undiscovered elements. But as discussed, this model of Mendeleev was also rejected. Now let's talk about what led to the rejection of the Mendeleev periodic table. Now, it's important to understand that at the time when Mendeleev came up with his periodic law and periodic table, atoms had not yet been discovered. But today, we know that atoms not only exist but also contain subatomic particles like the electron, the proton, and the neutron. This electron, as you have already learned in the last unit, is defined with the help of three important quantum numbers. The first one is called the shell number or the principal quantum number, which tells us the orbit in which the electron is present. The second one is the subshell, which tells us about the subshell in which the electron is present. This is also called the azimuthal quantum number. The subshell can be S, P, D, and F. And the last one is the spin quantum number, which tells us about the spin of the electron. These three quantum numbers basically tell us about the address of the electron inside the atom. We also know how the number of electrons and the number of protons in any atom or any neutral atom must be same to maintain electrical neutrality because, as you know, the matter around you is generally neutral. And this number, which is the number of electron or number of proton, which of course is going to be the same, is called the atomic number of that atom. This was a brief idea as to what we already know. Now, as you know, the Mendeleev periodic law stated that the properties of elements were periodic functions of their atomic weights. But the modern periodic law basically stated that the properties of elements were periodic functions of their atomic numbers and not of their atomic weights. Basically, atomic number was considered to be more of a fundamental property in comparison to the atomic weights. The main reason for this was that different properties of different elements was actually because of different electronic configuration of these elements. The number of elements in the neutral state of any atom, as you already know, is the atomic number, and that is different for each element, which actually causes the difference. And hence, atomic number was considered to be much more of a fundamental property than the atomic mass. And that is why the basis of the modern periodic law is the atomic numbers, unlike that of the periodic law given by Mendeleev, the basis of which was the atomic weights. This is the main difference between the modern periodic law and the periodic law given by Mendeleev. So the present periodic table that we have today is called the modern periodic table or the long form of periodic table. All the known elements which we know as of today, which is 118 elements, are present in this periodic table. This modern periodic table has a total of 7 periods or 7 horizontal rows and 18 vertical columns, which are called groups or families. The periodic table is also classified into 4 blocks, that is the S block, which forms the first 2 groups, the P block, which is made up of group 13 to group 18, the D block containing group 3 to group 12, and the F block, which actually should be a part of the D block itself, but that won't be possible because then we won't be able to fit the periodic table in one page, could we? Also, here on your screen you can see the total number of elements present in each period. The first period has a total of 2 elements, the second one has a total of 8 elements, the third also has a total of 8 elements, and so on. This was a very basic or a brief idea as to the long form of periodic table, but we are in for a much more detail. So let's go ahead and do that. Now, since we know what are groups, periods, and blocks, let's understand where they actually come from. Now, as already discussed and mentioned, atomic number is the number of electrons in any neutral atom and the basis of the modern periodic table. Total number of elements in any system also forms the electronic configuration of that atom. For example, if we talk about sodium, the electronic configuration of sodium is this. Now the numbers which you see here represent the shell number, the principal quantum number, or basically it tells us about the orbit in which the electron is going to be present. The S and the P which you see here represent the subshell in which the electron is going to be present. Now the highest principal quantum number that you see here is equal to 3, and this represents the valence shell. So the valence shell is the 3s shell which contains one electron. That is why it is having one valence electron. So in case of sodium atom, it is having 3 as the valence shell, S as the valence subshell, and 1 electron as the valence electron. Now why this electronic configuration is very important, you will realize it in about 2 or 3 seconds. Well, the valence shell actually becomes the period number. So since here the valence shell is 3, sodium belongs to the third period. The valence subshell, which is the S subshell, becomes the block. And since the valence subshell is S, sodium belongs to the S block. And since the valence electron is going to be 1 in case of sodium, it becomes the group number. Hence, sodium belongs to the first group. That is why electronic configuration is very, very important in the placement of any atom in the periodic table. And that is why sodium atom is present in the third period. It is belonging to the S block and it is present in the first group. Let's take another example. The electronic configuration of calcium is this. Since 4 is the highest principal quantum number, so it belongs to the fourth period. S is the valence subshell, so it belongs to the S block. And since there are a total of 2 electrons in the valence subshell, it belongs to the second group. Talking about carbon, this is what the electronic configuration of carbon looks like. Since 2 is the valence shell, it belongs to the second period. And since the valence subshell is P, it belongs to the P block. And now we have to talk about what group it belongs to, and this is when you have to clearly stop. When you have any element which belongs to the P block, you need to be extra careful. Here, the group number is not exactly equal to the number of electrons in the valence shell. Here the group number for P block elements is equal to 10 plus the number of valence electrons. Here the number of valence electrons, as you can see, is 4 because 2s and 2p is having 4 electrons. Hence the group number is going to be 10 plus 4, which is equal to 14. Now I have one question for you. Sulfur has electronic configuration which looks something like this. You have to come up and give me the answer as to what is going to be the period, block and group number. Now I hope all of us remember this series of filling the electron in various subshells. If not, you will have to brush up your knowledge of the first unit, which is the structure of atom. If you look carefully, you will realize that the S block starts with principal quantum number equals to 1, which means the n value or the principal quantum number value for S can be 1, 2, 3 and so on. That is why we have 1s, 2s, 3s and so on. For the P block, the minimum n value is equal to 2, which means the n value or the principal quantum number value for P can be 2, 3, 4 and so on, which basically means we are never going to have a 1p. For D similarly, the minimum value is 3 and that is why we don't have a 1D or 2D, and similarly for F, we will have a basic value of 4, which means we will never be having a 1F, 2F or 3F. What I basically mean to say is this, that the n values of S, P, D, F are the. Also the n shell or the principal quantum number which I have been saying is the valence shell and is also called the ultimate shell. It is the last shell in which the electron goes. The shell which is just next to the valence shell, which means one less than the valence shell, is called the penultimate shell. And the shell which is one next to the penultimate shell is called the anti-penultimate shell. So for example, if 4 is the valence shell, 3 is the penultimate shell and 2 is the anti-penultimate shell. Now let's talk about the general electronic configuration of various blocks. Talking about the S block, the general electronic configuration is NS 1 or 2. The last electron here or the valence electron goes inside the S subshell. In case one electron goes, it belongs to first group. In case two electron goes, it belongs to the second group. Talking about the p block, here the general configuration is ns2 np 1 to 6. Here the last electron goes into the p subshell. If only one electron goes, it belongs to group 13. If only two electron goes, it belongs to group 14, and so on. Talking about the d block, here the general configuration is n-1d 1 to 10, ns 0 to 2. Here we have an penultimate shell, which is the d shell, and a valence shell, which is the s shell. The n values here is 4 to 7, and I think you clearly know why. Because when n is equal to 4, then d value is going to be n-1, which is 3, and that is what is the basic thing, because d can never be 1d or 2d as discussed in the last slide. Again, in the f block, we have the general configuration as n-2f 0 to 14, n-1d 0 to 2, and ns2. Again, here we have an anti-penultimate shell, which is the f shell. We have a penultimate shell, which is the d subshell, and here we have an valence shell, which is the s subshell. The n value, the minimum n value is 6, because only then we will be having 4f, which is the only possibility. We cannot have 1f, 2f, and 3f as discussed in the last slide. But in the last slide, I discussed that the minimum n value for the s block should be 1. But here you can see that minimum n is 2 to 7 for s block. This is because hydrogen, which is a part of s block in this periodic table, is still not sure. Scientists are still not sure about where to place hydrogen in the periodic table, and in case of hydrogen we have n is equal to 1, and that is why here it is written 2 to 7, because hydrogen is not exactly considered to be a part of the s block. Now that we know what are periods, blocks and series, let's try to understand a little more. So the periodic table, as you all know, is having 18 groups. The first group is called the alkali metals. The second group is called the alkaline earth metals. The 16th group are called chalcogens. The 17th group is called halogens. And the 18th group is called the inert gases. The D block elements are called transition elements, mainly because it's a transition from the metals, which are generally on the left hand side of periodic table, to the non-metals, which are generally on the right hand side of the periodic table. The F block elements are also called inner transition elements and are present in form of two series, the 4F series, which is called the lanthanoids, and the 5F series, which is called the actinoids. Lanthanoids are called lanthanoids because they start from the element lanthanum, which is having 57 as the atomic number, and the actinoids are called actinoids because they start from actinium, which is an element which is having the atomic number 89. All the elements which are present after uranium are called trans-uranium elements and are highly radioactive. So the periodic table consists three types of elements: the metals, the non-metals, and the metalloids. On the left hand side of periodic table we have all the metals, and on the right hand side we have all the non-metals. In between we have something called the metalloids, which are also called semi-metals because they exhibit certain properties of metals and certain properties of non-metals. They are very important because they form what we call semiconductors. So it's quite clear to understand that as we go from left to right in periodic table, the metallic character keeps on decreasing or the non-metallic character keeps on increasing. So now I have a question for you. Which out of carbon and fluorine is more metallic and which one is more non-metallic? It's clear to understand that as we go from left to right, the metallic character keeps on decreasing. That is why fluorine is less metallic than carbon. That is why carbon is going to be more metallic and fluorine is going to be more non-metallic. So in this video, we came across the modern periodic law and how it was different than the periodic law. We discussed about the long form of periodic table and talked about what is period, group and block. We also talked about the general electronic configuration of different elements in different blocks. We talked about the general nomenclature of various groups, the alkali metals, alkaline earth metals, chalcogens, halogens and the inert gases. We also spoke about the difference between metals and nonmetals as well as metalloids. Now you all can head off to EduRef, practice the test and read the notes. We will meet in the next video. Thank you so much for watching.